Professor Jason Weiss is the Edwards Distinguished Chair in Engineering and the Director of the Kiewit Center for Infrastructure and Transportation Research. Before joining Oregon State as the head of the School of Civil and Construction Engineering, he was a faculty member at Purdue University for over 16 years, where he held the position of the Jack and Kay Hakama Professor of Civil Engineering and the Director of the Pankow Materials Laboratory. He earned a BAE from the Pennsylvania State University and an MS and PhD from Northwestern University in 1997 and 1999, respectively. He is actively involved in research on cement and concrete materials, specifically focused on early age property development, cracking, transport and concrete durability. Specifically, he is known for his research. His group has performed in the areas of shrinkage and cracking reduction, the use of the ring and dual ring test, use of electrical resistivity and the formation factor, use of internally cured concrete, and concrete pavement durability.
So thank you very much for that introduction, and hopefully everybody's doing well today. What I'd like to do is I'd like to talk a little bit about the role that slag can play in reducing pavement joint deterioration. And what I'll be talking about is some work that I've done with my colleague, Burkan Izgor, and we'll go ahead and we'll get started here. So to begin, I think, I captured this off of the internet, and I thought it was a good start for the week. If you haven't thought of your Halloween costume, remember safe social distancing, but a ready mix truck might be a way to go. And make sure that you use your concrete pumpkin so you're ready to go each year and are off for the holidays. But what we're really here to talk about today, as opposed to Halloween decorations and getting ready and doing those sorts of things, is really pavement joint deterioration. And I want to start off by saying that the vast majority of concrete pavements perform very, very well. There are some, however, where the joints start to fail, and they start to fail prematurely. And when we say prematurely, this is around the 10 to 15 year mark. So the challenge with this is typically you're designing these pavements to last 35 to 50 years, but when they start having these problems at the joints, as you can see here, or you can see here, right, this starts to become a big problem because you have an otherwise healthy pavement that's performing exactly the way it's supposed to be. And now you have to get out and you have to repair it at a cost of about $1 million per mile. Plus you're putting workers into a difficult situation if you're maintaining live traffic. And it's a very difficult repair to do because it's not sufficiently deep, it's not sufficiently wide, and trying to get that repair to stick is a bit of a challenge. So when we first started to see this, the project that this popped up on is shown over here. And this project popped up about 11 years after the project had been put in place. And what was particularly alarming about this project is this was a National Quality Award winner. We had all the data from this project and showed that the performance, at least in terms of meeting the specifications, was excellent. So the question really became, why was this damage happening at these joints? And what's interesting is if you look here, you could actually just put your hand right into the joint and you could pull out the concrete just with your hand. The other thing that was a little bit telling is it hadn't rained in weeks. And when we pulled back, we didn't really have to pull it back. When the joint sealant helped us out and jumped out of the joint, what we could notice was that there was standing water even after 2 weeks sitting in this joint. So we're going to come back and we're going to talk about how both of those things can happen and can really drive or exacerbate this problem. Now, what I'm going to talk about is really salt damage at the joints, and this is actually covered in something called performance engineered mixtures approach that FHWA is taking. It's also in their performance related specifications code that's coming out. So there's really a lot of push to really try to make sure that we design mixtures that are able to withstand this type of damage. We now have new quality control and quality acceptance procedures. And what I want to talk a little bit about today is the role that slag plays. Not to be left out of the party, ACI has also published a technical note that talks about this joint deterioration due to these chloride-based de-icing chemicals, and you can get that. The technical note is listed up here, and everything that we talk about is going to be consistent with what's inside of this with this note. So again, just coming back to this, our problem today is to really start to look at why these joints are falling apart, and really how we can design these joints differently from a materials perspective to be less susceptible to this type of damage. So the first thing that I wanted to mention was we had to move toward a working mechanism of what was happening. You know, when we first started the discussion, everybody sat in a room, and I think everybody on the call has probably sat in one of these rooms where everybody sat there and they pointed a finger and they said, I don't know whose problem it is, but it's not my problem. All right. There were discussions that this was a contractor issue because they were over vibrating the mix, or they had a bad mix design, or they didn't have the right amount of air. There was a discussion that it was the pavement designer's problem because there was too much steel that was keeping the joints from opening. There was bad drainage. The pavements were too thick. There was a whole discussion about the deicer supplier. So maybe it was just some sort of super salt that was eating the pavements, and we needed a new specification for salt. Not to be outdone, the admixture suppliers got brought in, and they were told that they had bad air systems, and if they just had better air, this problem would go away. There was a whole big red herring about hand placements versus machine placements. And what I do want to point out is this is kind of an interesting discussion because it was how the material was delivered. But what we ended up finding out is it wasn't necessarily hand placement versus machine placement. It was actually a change in the mixture when they went to hand placement that was really the issue. And we can get into that. But the real issue here is anytime that they wanted very high early strength, it turned out that those mixtures were more susceptible to damage. It was sulfates, it was ettringite, there was anti-icing practices where they're now pre-salting the material. There was a group that believed that this was nothing more than decracking or ASR. Then also the saw cutting crews, they got drawn into the mix, except for the fact that you see this both at saw cut and formed joints. So really the question is, what is our working mechanism for really what's happening in this system? Well, what I want to do is I want to point out at the top right-hand corner, this is a happy joint. This is the joint exactly how it was designed and exactly how it was expected to live its life, right? The idea is you come in with your first saw cut. This would be your first saw cut. All right, you do that early so that the crack can form. The crack forms, the width stabilizes. You come back in with the second saw cut so you have a nice uniform width. You can then put in your backer rod. You put your sealant on top that's properly cleaned and adhered to the surfaces. And then whenever you get moisture on the surface, this sealant keeps the moisture out. This joint is happy and everything works really, really well. Well, one of the challenges is, while this is great and this is the way it's been designed, this is frequently not how this is working. And there were a couple things that were pointed out. First, a lot of the non-absorptive backer rod actually absorbed water, and that was a big issue. So water was entering the joint and that water was being trapped. So part of the reason that this was entering is a lot of times these sealants were starting to fail. And there's a couple different reasons that the sealant and backer rod may not be working very well to keep the fluid out. It turns out that there's a potential chemical reaction that's going on there, but I also believe that most of the time it's just the way that the material is being applied in the field that's really leading to a challenge. The idea here is that fluid, and I want to be very careful that I'm going to call it fluid now as opposed to water, because fluid is going to denote the idea that it's water with stuff in it. And that stuff is the de-icing salt. And the real issue is the water and the de-icing salt get in here. They can saturate this bottom portion of the concrete, which can lead to freeze-thaw problems. When if you have a very high degree of saturation, you can actually see the system get damaged down here in this red zone, and this thing pops out that looks a little bit, I don't know, like the state of Nevada or California maybe. All right, the other issue you have is a lot of times you see this flaking coming off of this wall at about 3 to 6 millimeter depths. And this is pretty common, and this is seen in a lot of these pavements. So as we went to try to study this, we collected a couple samples from the field. Here you can see an actual paved sample. This was being ready to be put into the freeze-thaw environment. And a funny thing happened on the way to put it into a freeze-thaw environment. What you saw here was that this damage really blew up at this particular joint. And the thing that's interesting about this is, you know, when we first showed people this, they said, see, exactly, we told you it was a freeze thaw problem. The funny part about it is this never actually went into the freezer. So this was a sample that was ready to go into the freezer and blew up the week before it could actually go into the freezer, just with the soaking solution on it. So now the question is really really what's going on. We see that for about 15 years, after about 15 years, these pavements start to show damage. There's been a lot of speculation, as we've mentioned, as to the cause of this. We've come a long way, we think, to solving this. And there's a lot of really interesting approaches here. So I'm going to take you through several steps of the timeline that we've been on sort of researching this problem. We're going to start out in a couple seconds here to talk about what the problem is, because it's a newish type of problem that people haven't seen before. Because of this, we actually had to develop a little bit of what's called phase diagrams or phase isopletes. This is going to be a little bit of science that I think is important for people to see, mainly so that they see when there's the wrong science or maybe incomplete science being shared with them. Right, we're going to talk about a test that's going to quantify the reaction. We're going to talk about some potential solutions. Right, there's been field testing, specification language, and concrete proportioning procedures that have been developed. I'm not going to go into these in depth, but I'm going to give you the sort of the bullet on these, or the rule of thumb on these. And I am going to talk a little bit about the role that predictive thermodynamics model and reactive transport models can really start to play in this, because this really now starts to let us take the whole design process to a completely new, and I think a completely exciting level. So to get started, what I want to do is I want to talk about the possible reactions that are taking place. So on the East Coast, it's 10 o'clock, it's a Monday morning. What we all want to see is a phase diagram. All right, so if you're not familiar with phase diagrams, don't worry about this. We're going to walk through this pretty slowly. But if you went to the website and you searched out a calcium chloride water phase diagram, you would get a diagram that looks like this one. Not as nice as this one, but it would look exactly like this one, where you'd have salt concentration plotted along the x-axis. Along the y-axis, you'd have temperature, and there would be a couple lines on this graph. Now, what we would notice is if we're at a high temperature, right, that solution is just salt water. Right, so at a high temperature, 60 degrees Celsius, right, we're sitting up here and we just have a glass of salt water. As we start to drop the temperature, it stays a glass of salt water until we hit this line here. And once we cross this blue line, we've gone across something called the liquidus line, right, where all of a sudden ice cubes start to precipitate out of the solution. So now what's happened is, as we go across this line, ice cubes start to form, and the ice has a very, very low solution. So the ice has a solution that has about a 0% concentration, right, while the salt water gets saltier and has a higher concentration. All right, so the salt is getting saltier, the ice is getting more and more pure, and this is what happens until we drop down below about, for calcium chloride, it's about minus 52 degrees, and at that point, all of the salt water becomes something called a eutectic solid. Now, it was important for us to trace out this bottom line, although we think in most cases we're not crossing this bottom line, and a lot of the action is happening up here a little bit higher. So if you go anywhere in the country, you go on the internet, you look for this, you will see this website. If you talk with a lot of salt producers, they will show you this phase diagram, usually because they're showing you their salt has a lower liquidus line, which is great because that means that the salt is more effective in melting the snow and the ice, which is what it's out there to do. The challenge with this is that this is not necessarily a complete picture of what's happening. So I'm going to get into the equation of what's happening, and then I'm going to show you how that phase diagram has to change in a couple seconds. So this idea is we can get this thing called calcium oxychloride to form. Calcium oxychloride is a little bit scary. The first reason it's scary here, as you see, is this great big equation. All right. The second reason that it's scary is it forms with things that are inside of our concrete. So the idea is we have calcium hydroxide, and it's going to react with the calcium chloride. This could also be a magnesium chloride because the magnesium will have calcium substitute for it. But I'm going to stay focused on calcium chloride right now and water. And it takes these three components and puts them together and forms this thing called calcium oxychloride. Now, calcium hydroxide is a byproduct of the cement reaction. There's two things that form. There's calcium silicate hydrate that forms, and there's calcium hydroxide that forms. This is the calcium hydroxide. We always get it when OPC, ordinary Portland cement, is reacting. The calcium chloride is coming from our deicing salt, right? And it forms this really long equation. So the first reason it's scary, long equation. Second reason it's scary is we have all the pieces to make this inside of concrete. The third reason that this is scary is this is really expansive. Not expensive, expansive. This means that it's about 303% larger than the original calcium hydroxide. Now, in concrete, we freak out to design what happens when water freezes because it expands by about 9%. This is a 300% volume change. So as you might expect, accommodating that 300% volume change is really, really difficult. So what I want to do is I want to come back and I want to take our phase diagram, because that was so much fun to discuss before. And I want to say that while the calcium chloride water phase diagram was really interesting and is that blue line that we saw before, the problem is we have another player in this space. And when that other player comes into this space, namely the calcium hydroxide, we get an additional line on this diagram that makes this more complicated and gives us more that we have to think about and more that we have to look about when we start designing these systems. So the whole idea now, again, when we're at high temperature, we still have salt water. The issue, though, is once we go across this orange line here, now all of a sudden, instead of ice cubes coming out, we get this oxychloride phase that starts to come out. The thing that you should pay attention to is the temperatures at which this is happening. So this is happening not below freezing. This is happening anywhere between about 0 degrees and about 30 degrees. All right. And this means that this is happening in the spring, in the fall, in the summer, in the winter, right? So while you may be in a place that has 100 freeze-thaw cycles, it may have 1,000 calcium oxychloride cycles, because of the temperatures that are happening, all right, as you go up and down over this line. And each time you go up and down over this line, and now it spells ow, and it's not supposed to spell ow, but that's exactly what happens. Each time it goes up and down over this line, we get the oxychloride to go away, it starts to come back, it goes away, it comes back, and each time that starts to happen, we start to create that expansion, right? If we continue to drop the temperature, we get more and more oxychloride, right? We drop it low enough, we now start to get the ice forming, and if we go low enough, now we get the eutectic solid that forms just like we saw before. So the real issue here is in this bluish purplish region, we're now starting to get a large amount of oxychloride that's forming in these systems. And it's that oxychloride that is presumed to be the cause of a lot of this damage. Now, I will also say that this oxychloride is a little bit tricky to see. It's a little bit like tracking Bigfoot, right? You can see that Bigfoot's been there because you've got a blurry vision of it, or you've got a footprint somewhere, or you've seen that, you know, he's broken in and he's stolen your beef jerky or something like that, but you don't usually see Bigfoot himself. It's the same way with the oxychloride. Because this is sensitive to moisture, so it's sensitive to RH. It's got to be a very, very high RH. It's got to be exactly the right temperature, right? You may see that the oxychloride was there, but the oxychloride can be difficult to find, although I think I have some pictures of some really, really pretty oxychloride crystals later on from Carl Peterson's work in this field. Now, one of the things that I want to mention here is that supplementary cementitious materials, particularly pozzolans, can be very, very good at reducing the problem for this type of damage. All right. I am going to come back to this in a second because slag is not necessarily strictly a pozzolan, but I want to just mention sort of what the mechanism of this is and then start to talk about what's happening when we put slag into the system. The idea here is, again, this is just the equation that we saw earlier, right? We've got calcium hydroxide, calcium chloride, and water coming together to form calcium oxychloride. Anytime we start to replace the cement with an alternative cementing material, we get the benefit of dilution. So if we take out 30% of our cement and replace it with 30% fly ash, we see that we have 30% less calcium hydroxide. If we have 30% less calcium hydroxide, we expect the oxychloride to go down by about 30%. This is what we're going to refer to as dilution, and it's this green line that we see over here. So as we move left to right, we're increasing the amount of fly ash in a mix. And when I say increasing the fly ash, I want to be really careful. This is not just adding fly ash to the mix. This is taking cement out and replacing it with fly ash. I'm going to plot this as oxychloride in a second, and I'll explain how we make this conversion in a second. But the big part of what we see as we move left to right is dilution. Now, when you have a fly ash or a silica fume or a pozzolan, you'll see that there's also a pozzolanic reaction. And this is because we know that the calcium hydroxide is going to react with the silica or the alumina in the system, and it's going to form either CSH, all right, or CaSH. And you may think that it's great to have cash in the system. It is great to have cash in the system and CSH in the system, primarily because it reduces the amount of calcium hydroxide that can participate in this reaction. What we've noticed here is that this bluish area is really what we typically refer to as the pozzolanic portion of this, and we get down to the overall behavior, which is really this red line. Now, we know that there's always going to be some calcium hydroxide in the system, and we actually want calcium hydroxide because it helps to provide a buffer for the steel to be resistant to corrosion. However, the real issue is if we can get down below, somewhere around this purple line, we start to see that problems really go away in the field. So anytime we're below the purple line, we see a lot less problems than if we're way up here. So again, plain system, we've got 35 grams per 100 grams of paste of oxychloride. When we get up to about 35% fly ash replacement, we notice that we've cut that down to about half of its original value. So what we're saying is if you're starting to use fly ash or you're starting to use classic pozzolans, you want to be at a slightly higher dosage than what we're typically using. Right? As I mentioned before, we can go through and we can actually, we can write an equation that relates the calcium oxychloride on our y-axis to the calcium hydroxide on our x-axis. And if you write this equation out and you do all the chemistry, you find out that this should have a slope of about 2.47. Let's get rid of this this is a 2.47 that wasn't colorful enough and it just didn't get erased. All right, but you'll see the theoretical line is this orange line. The practical line and all the data is shown over here. All right, and the one reason that we see all of this over here is there's a little bit of an offset because some of the calcium hydroxide will get sort of placed into a reacted shell. So while you still have calcium hydroxide that's maybe at the heart of the system, the calcium chloride can't get to it very easily, so you don't see the oxychloride forming. This can actually be substantially greater if you have a system that's carbonated. For example, carbon dioxide will do the same thing, right? Or if you have a smaller calcium hydroxide crystal. So this is one of the reasons why we've sort of said just measuring calcium hydroxide isn't enough. And there are people who are running around saying, well, if we do a TGA and we measure the calcium hydroxide, that's enough. We know how much calcium hydroxide is there. Maybe, but the challenge is you don't know if that calcium hydroxide is available to react with the system. We'll see with carbonation, we'll see with sealants or topical treatments later that that may actually be an issue. The thing that's really important, though, to take away from this graph is shown right here. You can see that we've got a whole bunch of these red dots. The difference between the red dots and the squares, these red dots are straight up OPC. The squares over here are OPC with something else in it. So not surprisingly, as we said before, if we start replacing some of the ordinary Portland cement with an alternative cementing material, fly ash, slag, silica fume, metakaolin, rice husk ash, all sorts of other things, we'll notice that this material starts to have less calcium oxychloride. So what we want to do now is we want to start to talk a little bit about the test methods that are out there and that have been developed to really start to look at this. So the first test method is going to be actually a very simple type of test method. This has been standardized by AASHTO now, and this is a test method to look for the maximum amount of oxychloride that could be created. I want to point out that, there's been a lot of people who've asked, well, does this relate to, exactly what's happening in my pavement in XYZ state? And the answer is no. This is a standardized test that's designed to have standard boundary conditions so that we know how much oxychloride can possibly form in the system so that we can design mixtures that'll have less oxychloride that are forming. So the idea behind this test is we take a cement paste and we hydrate it. We usually do this under accelerated hydration. So we do this at a high temperature for 28 days because what we want to do is we want to get something that's mature. We want to get something that has a 98-day equivalent degree of hydration. The reason for this is you're most susceptible to calcium oxychloride at later ages. All right, so you want to provide time for that calcium hydroxide to form. You also want to provide time for your supplemental cementitious material, specifically if it's pozzolanic material, to react with that and reduce the amount of calcium hydroxide in the mixture. We then take this ground material and we put it into a little tiny, it almost looks like a little tiny beer can, and we have an empty beer can. So I've done these backwards, but this is the sample and this is the reference, and they'll go into these little tiny beer cans that'll sit, all right, on these platforms. And we're going to measure the heat difference between the one that has the ground up paste in it and the solution versus one that is completely empty. So by measuring the heat difference, we're going to be able to start to use this to describe some of the behavior of the system. Now, what we do is we take the sample at 23, 25 degrees. We use 25 degrees to prevent condensation while things are sitting in the lab. We drop the temperature down to minus 90 degrees. There have been a few people who said, well, why do we go to minus 90? It never gets that cold in my state. The reason we go to minus 90 is we want to freeze everything in the system so that we can quantify the amount of eutectic, the amount of freezable water, and the amount of oxychloride that are forming in the system. We do this little jig at the bottom because by doing the jig, we make it so that it's more likely to freeze all the material. And then what we actually do is we heat the material up at a constant rate. We use a relatively slow rate because all of these phases are difficult to detect. And by going at a slower rate, we're able to detect these materials. Now, there have been some people who said, well, this test takes way too long, all right? The test can take a long time, but it doesn't really matter because the machine's doing all the work. You put the little capsule in the machine, you walk away, you come back 8, 10, 12, 14 hours later, and you have the results. So you don't have to do anything. I mean, you can watch the machine if you want, but it doesn't really matter because the machine's going to work whether you watch it or not. The real takeaway, though, is not this plot because this is what we're telling the machine to do. The real takeaway and the beneficial thing is this plot. All right, so on our x-axis, we have temperature. This is the temperature of the sample during the heating cycle. On our y-axis, even though I've hidden it here behind these words, this is heat flow. This is the amount of heat that's being given off. And if you look really closely at this graph, all right, you will see as we start to move in this direction, we see 1, 2, 3 peaks. And these 3 peaks, all right, start to correspond with different things that are happening in the system. The first peak happens at about minus 53, 52 degrees. All right, this peak at minus 52 degrees refers to the eutectic solution, which is that really, really concentrated salt solution. And if you go all kinds of wild and you integrate the curve to find the area under this curve, this tells you exactly how much eutectic solution there was in the system. The second peak, which goes from about minus 50 degrees up to about 0 degrees, all right, is the ice that's inside of the system. And again, if you find the area under this curve, this tells you the exact amount of water that's inside of the system that became ice. The third curve, and big hint, this is the one that we're after, is the oxychloride curve. Now, this is going to happen at higher temperatures. It's going to happen around 35 to 40 degrees, all right, for the concentrations that we're looking at. And the area under this curve, all right, tells us the amount of oxychloride in the system. So if you want to reduce the potential for oxychloride, you want a smaller this curve. If you want a lot of oxychloride, you increase this curve. I don't know why you'd want a lot of oxychloride, even though there was some work in the nuclear industry that said this could be a good thing because it blocks the pores. It does block the pores. The problem is it starts to create the concrete falling apart. So let's stay away from any reason to increase this. And now what we're going to do is we're going to look at solutions that minimize this curve. If we can minimize this curve, we know that it's going to be resistant to salt damage. Now, what's the benefit of this test? And some people have said, it takes 10 hours. It's a really long test. Let's think about this and compare this. It takes about 10 hours, and we have a quantitative measurement of all the oxychloride that can form in the system. That said, if we were to run a salt damage test by placing a cylinder into a salt solution, we're looking at something around 3 months. All right, so we're saving an enormous amount of time by doing this, and we're getting a very quantitative measurement. We're getting an upper bound, so we can use this for design, and we can do this very, very quickly. So if we start to look at some of the common materials, and this is where it's going to become really interesting for our slag enthusiasts in the audience, we can look at a couple of these different materials and we can start to see how they behave. Again, our x-axis is SCM replacement level. Our y-axis is the amount of oxychloride. Again, we're at 0, 0 here. This is a plain OPC system. And what you'll notice is we see again that dilution. So if we took cement out and just put limestone into the system, right, we would see that the oxychloride decreases primarily because of dilution. So while the orange line is our dilution line, we get really, really close with our limestone. We talked about fly ash and silica fume, right, that are the pozzolanic reaction with silica. We talked about our calcined clay, which is the reaction that happens with alumina, right? The really interesting line here, though, is the slag. So what's interesting here is slag is not undergoing a pozzolanic reaction, but slag goes pound for pound with fly ash, and they're very, very similar. So what you can see is the data kind of falls out into 3 categories. Inert fillers, right, or nearly inert fillers, before anybody gets really excited, because limestone does do some stuff. It's nearly inert fillers, right? Really, really reactive materials, metakaolin and silica fume, right? And then we have sort of the classic ones that are the most used in the cements world, which are fly ash and slag, and they sort of follow this line. Now, I can read people's minds, and people are saying, oh, you've shown us that it's fly ash, but which one is it? Is it C or is it F? Yes. It's C and F. They follow along the exact same line, right? There's differences in what they're doing in their reactions, but they're very, very similar in terms of their behavior on this particular graph. So the big takeaway here, fly ash and slag are going to work very, very similarly and have sort of similar replacement levels, have similar levels of performance. Right? But let's dig in a little bit deeper and see what's going on. Now, here's what I wanted to talk a little bit about, and this is something called thermodynamic modeling. And I don't want to get into all of the details, and this is really a lot of the work that Burkhan Isgor and his group are really doing a great job on. And what I'm going to try to do is I'm going to try to explain this and see if I can get most of the pieces of this right. But what I want to do is I want to explain a little bit about how we can minimize the energy computationally to determine the types of phases that are going to react and be present. So if we look at this, if we're at 0 degree of hydration, we're way over here on this axis, 0 degree of hydration is our x-axis. The volume of the materials inside of the system is shown here on our y-axis. This is really water on the top of our graph. This part on the bottom is really whatever powder we have in the system. So this could be cement, this could be cement plus slag, right? And you could put the chemistries of the material into this program, and then there's an enormous amount of math that's going on in the system, right? But what they're gonna do is they're gonna predict what happens at an infinite time in terms of all of the things that are reacting. So what people do who want to do work in the cements area, they realize we can't go to an infinite amount of time. So they've developed kinetic laws that allow you to determine what's the degree of hydration in the system. And by doing that, you can say, well, if I go to 70% hydration, I could now see what's left in the system. I can see how much water's left in the system. I can see how much cement is left in the system. I can go into this and I can start to look at what are the reacted phases that are taking place in the system. And the one reacted phase that I can really start to get into here, so we've got some CSH right here, and we talked about that before. And then this green area is our calcium hydroxide. Right? So we can actually use this whole thing to measure calcium hydroxide. And one of the real takeaways that we have to look at is we have to look at if we replace a certain amount of the system by slag and we measure the amount of calcium hydroxide that's forming, what we can start to see is the amount of replacement and the reactivity are very important in determining the amount of calcium hydroxide that's inside of the system. So if we have 0% reactivity, this means our slag is completely inert. We're going to follow along this black line, and we have that dilution curve, right? This is that exact same curve I showed before, where I had this flat line and I said this first thing was dilution. That's what happens if the system is completely inert. If the system reacts 100%, we're down here along this red line, right? And what we know is that reality is we're going to be somewhere in between. Now, I'm going to sort of give you the answer here, and then we're going to come back to it. Most of the time we measure slags, we're in about the 60% reacted range during normal types of hydration that we're interested in. So we're going to be somewhere between this aqua line and this pinkish purplish line. All right. But in reality, what you'll notice is if we want to be below 15, we want to be in this range of 15 to 10 grams of calcium hydroxide in the mixture to reduce this problem, right? And we're at 60% reaction. We need to have a replacement level that's somewhere between about 18%, right? And if we come down along this line down here, we may get out into the 40 to 50% range. Now this sets up almost perfectly for slag usage. So the whole idea here is when we're used to using slags in these systems, we're used to using it in these higher ranges, 30, 40, 50%. And you can see here when we're up in the 30, 40, 50%, we have exceptional performance when it comes to reducing the damage that's inside of the system. Now, if we start to look at this, what we can see is that there's a huge volume change, as I mentioned. That volume change happens right as we go across this line. So if you look at this graph on the right-hand side, temperature versus volume change, high temperature, we drop down below 40 degrees, we get to about 35 degrees, and all of a sudden we see this 300% volume change. We heat the system back up, that volume change goes away. All right, so we really are seeing now that that huge volume change is real. And if we want to see what that starts to look like, here we can see some pictures from Carl Peterson, again, capturing Bigfoot in the forest here. We can see the calcium oxychloride that's forming. But here's what happens if you just put cement paste systems into a calcium chloride solution. I believe this was for about a week or a week and a half. That just breaks up on its own. All right, so if you look at flexural strength, and this is a very simple flexural strength test, it's called the B3B test, right? What we do is we make really simple little cylinders, the material, we cut them flat, and then we expose them to different solutions. We put it on a single ball on the top and then 3 balls on the bottom, right? And you can measure the flexural strength of the system this way. It's a really, really effective test to look at chemical damage. What you notice is when you don't have fly ash in the system or SCMs in the system, right, you see that as the calcium chloride concentration increases, the strength drops off dramatically. So when you get up to higher concentrations, and this was a relatively short period of time, you see that the strength drops off instantly. The other thing I want to mention here, because I'm sure that people are thinking this, they're saying, well, you know, normally when we do testing with salts, we're down here. Why are you way up here to do this type of work? Remember, our salts are sitting in those joints, and what's happening is we're adding the salts, and then we're getting evaporation. We're adding the salts and we're getting evaporation. We're adding the salts and we're getting evaporation. So this solution becomes very, very concentrated over time. Now, if we go back to our thermodynamic model and we look a little bit at what happens when we start putting slag into the system, there's some really, really interesting things that start to happen. So again, just a little bit on how we read this diagram. On the bottom, what we've done here, and Keshav has done a great job of sort of assembling all this information. We've done this at about 80% hydration. And what you'll notice here is that we've got unhydrated part of the system that's down here. So this is essentially the unhydrated cement and the unhydrated slag that's in the system. We've got the limestone that's sort of remaining over here. And what we have is we've got 0% limestone, 3% limestone, and 15% limestone. with slag in the overall system. So we're varying the amount of slag as we work from one side of this graph to the other. You'll notice that we've got our CSH that's forming here in the brown. All right, we've got our porosity that's up here in the pore solution that's shown here. So our porosity is going to be pore solution plus the chemical shrinkage, the blue and the orange on the top. And what's really interesting now is as we start to add the limestone into the system, we start to see really different types of phases that are taking place. So when we had no limestone in the system, what we can see is we get mostly monosulfate, all right, and we get Portlandite or that calcium hydroxide. Portlandite is just a fancy calcium hydroxide over here, that thing we're looking for and trying to reduce, all right? As we start to work our way across the system, we can see additional reactions that are happening, particularly when you have the limestone in the system, mostly in changing the monosulfate over into carbonate phases and ettringite phases. So this really happens around 2 to 3%. We see most of this going away. By 4%, we see this whole green bar has gone away completely. And by higher concentrations, where we get to like 595 cements, we see that we essentially have no monosulfate left in the overall system. The real takeaway, though, is we also have substantial reductions in the amount of calcium hydroxide that are going on in the system. And if we reduce calcium hydroxide, we reduce oxychloride. These phases will also help to bind some of that calcium chloride, which can be really, really effective. We'll notice that as we add more limestone in the system, we reduce the porosity in the system. So this is a plot of porosity on the right-hand side. We reduce the calcium hydroxide, which we see on the left-hand side. So we see a synergy. Adding the slag plus adding the limestone gives us lower amounts of calcium hydroxide. All right. We also see that by adding the limestone to the system, we can reduce the porosity of the overall system, which is overall really, really good. Right. I do want to just mention really briefly here, because I want to wrap up so that we have plenty of time for questions. Again, the whole idea is we can use this test, reactivity test. The reactivity test can be super beneficial. Even though we're not dealing with a pozzolanic material, it can help us to determine the amount of reactivity that's in the overall system, and that can be really, really useful. As I've mentioned before, this can be very beneficial with Portland limestone cements. And I'm going to go through this very quickly. But when you put slag in with Portland limestone cements, here you can see the slag shown in orange. You can see our OPC shown in white and our limestone here shown in yellow. There can be some real beneficial effects. As Matt Shai showed, and as we've shown with that thermodynamic modeling, what you can really see is you can see that the porosity decreases substantially and then comes up a little bit because you're getting a little bit more porosity in the system. But by producing and changing some of those phases, you can have some real big benefits in the overall system. Again, here's some examples of some of the great work that Doug Hooton's done in Canada, where he's showing the use of standard cement with slags and seeing some really good benefits. As I mentioned before, one of the real big benefits that we see is we're getting different reaction products. And where this can really be beneficial is really shown here. So this is a mixture where we have a normalized strength. This is Portland limestone cement system over an OPC system where you've got slag in the system. By adding the slag and limestone together, we see much higher strength ratio, which means that the PLC with slag is more effective than the slag and OPC on its own. So the limestone really helps to reduce the porosity. This takes us back to this type of diagram we see over here, right? We've seen this before where, again, we have porosity in our plane system, but as we start to put limestone and slag together, we really start to see this change in the phase assemblage. We actually see a slightly faster reaction, which has been seen by Barbara and Lochenbach and her group in Switzerland and put into some of this GEMS modeling as well. But we see a reduction in the porosity. By reducing the porosity, we increase strength. We also increase the rate of reaction that's happening. So you can see that strength gain is much higher at these early ages, all right? And this can be really beneficial in these overall systems. So again, just to wrap this up and to provide some conclusions, and then we can go ahead and start to take questions. Salt damage is occurring in concrete pavements, specifically at the joints, because we get salt water that's sitting in those joints and becoming more and more concentrated over time. The calcium hydroxide is going to react with the calcium chloride, all right, and water. And when it reacts with calcium chloride and water, it produces this calcium oxychloride, and this calcium oxychloride is expansive and can create damage. Slag is incredibly beneficial because it reduces the potential for damage to occur. This occurs primarily because of dilution, and the dilution as well as additional reactions will reduce the amount of calcium hydroxide in the system. Again, by doing this, the really exciting part of this is we want to be somewhere between about a 20% and a 50% replacement. Higher replacements are good. And this is really an area where slag lives and works really, really well in that 30–40% replacement level, which is great and can be a great solution to this problem that we see in paving. So more paving mixtures with slag would be a great, great thing. We talked very briefly about the reactivity test. While it's been designed for pozzolanic materials, it also shows benefits of slag in terms of reducing the calcium hydroxide. We talked about the low temperature differential scanning test. This is very useful and can help us to describe the overall reduction in calcium oxychloride. It can be a very useful screening test. I think you've seen that the thermodynamic models, although they can be very complicated, they can really show us some very interesting things about what's reacting in the system. And finally, by way of conclusion, limestone and slag together are much more effective than just the slag on its own. So if we're going to be looking at solutions that lead to sustainability, lead to improved durability, lead to the direction that we want to be going as a field, combining Portland limestone cements with slag, ASTM C595 cements with slag can be a great combination and can be really beneficial because of those reactions that are taking place in that system. And with that, I will turn it over to our hosts to see if we have any questions or comments. And thank you very much for listening. So Drew, any questions or comments? I'm looking and I'm seeing.
Thank you for Professor Weiss. Great presentation. Let's see if we have any questions come in. The first one here, did you study replacement ratios higher than 50%? If so, what did you find?
I'm sorry, could you ask that one more time?
Sure. Did you study slag replacement ratios higher than 50%? And if so, what did you find?
Yeah, so at levels greater than 50%, you'll see that that reduction continues to happen. Once you get above 50%, though, you may get into some issues of constructability, right? But if you don't have those issues, you could go much, much higher. You'd see the amount of oxychloride would reduce even further. What we have noticed is that once you get below a certain threshold, you can really see some huge benefits. Okay, and that threshold is that 10 to 15 gram number. Once you've seen those benefits, you've kind of done away with the problem. So if you want to use more slag, there's nothing stopping you, and it's great from a sustainability perspective. And so go wild. There's no deleterious reaction due to this that happens at higher concentrations.
All right, thank you. This kind of is in the same wheelhouse here, but the next question is there a minimum substitution of slag that should be used that may not need to be tested by the AASHTO test?
The answer to that is yes and no. I don't know that anyone is specifically stating, this amount should be used or this amount should be used, and therefore from a specification perspective, you don't have to do it. But if you're in that 40% range, 40% replacement, I think from everything we've tested, and again, I want to go back to Drew's great disclaimer, don't trust the author saying anything for mixed design, all right? Usually when you're above about 40 to 50%, you never have this problem at all with any of the slags that we've tested, okay? But it's a relatively simple test, and if somebody wanted to see it tested, I'd be happy to take one of your slags and cements and run the test for you.
Right. Thank you. Another question here. Some researchers have shown that salt scaling, surface scaling, is a problem for high slag concrete. Could you please explain why it's different than joint scaling?
Yeah, so the slags, so the surface scaling can or cannot be a problem. What we've found is that's mostly related to the finishing of the system as opposed to necessarily the chemical composition of the system. We believe there's a huge benefit in terms of the things that you do to reduce joint damage in terms of what can help to reduce scaling. In most of the studies that we've done, and this is going to sound like a really odd correlation, but we've found that scaling is frequently related to something like slump. It's frequently related to how workable the mixture was. And many times what's happening is the surface is settling differently than the rest of the system. The other thing that I want to come back to, and I can show a picture at the end if we want to look at this, but one real issue that you can get into is making sure that you've provided sufficient curing for these systems. So in general, what we've seen with slag systems, if they're well cured, and we have a really good way to measure the curing efficiency that I just didn't get to today because of time, if they're well cured, if they're relatively low slump like we see with paving mixtures, it's very difficult to get these mixtures to scale. However, if you get them too wet and you get a highly porous surface, or you overwork the surface, you can have problems with scaling. What I would recommend is using something like a topical treatment, because that can actually help in both cases and can make your system resistant to scaling and resistant to salt damage.
All right. Next question here. Were the flexural strength specimens paste or mortar specimens?
These are paste samples, John, and you know, we see similar things when we get into mortars and concretes, but the really nice part about this is when we use paste samples, we can test these much quicker because we're getting a lot of surface area exposed for the reaction.
All right. Next question. When using slag, is there any benefit from pore size distribution modification in addition to chemical benefits related to removal of CH?
Yeah, that's really a great question, and that kind of comes back to what we were seeing here with the thermodynamic model a little bit. So the first thing is we see that overall there's less porosity in the system. The second thing that we notice, especially when it's interground, you get a better blending of those materials, so you really do reduce the pore size distribution. The one thing that we have noticed is, and this is a little bit deep here, but as we get into the SCMs, once you start to add fly ash, you'll see your connectivity goes way down really quickly. We see that the slag is a much more gentle distribution, and we think that this has to do with essentially the fact that you're not reacting with as much of the calcium hydroxide in the system, but that's a really good question.
All right. Next question. In terms of durability, how does slag affect chloride diffusion and sulfate attack?
Well, again, anything that we're going to be doing to decrease this connectivity term, this beta term that I've just sketched out here, anything that we do is going to make it harder for those chlorides to go into the system. It's going to make it harder for those sulfates to go into the system. And this is really where we would do a measurement like a resistivity or a formation factor measurement. So what we see is as we use slag or as we use any other SCMs, we see that those become much more resistant to the diffusion of ionic species. We also notice that those materials are going to be more likely to be bound in those systems. But I'd be happy to answer that question, that question in more detail if somebody has some more specific questions.
Next from Jared Wright. These are very interesting results and coincide with what we are seeing in the field. Due to recent extreme temperature fluctuations in the spring and fall months, it is not uncommon to see 20°F weather one week and 80°F plus weather the next week. This leads to owners salting their concrete at 20 degrees, but then to salt experiencing 80 plus degrees and undergoing the reactions mentioned in your presentation. Do you have any recommendations for appropriate de-icing techniques?
Yeah, so the challenge here, Jared, is the de-icing techniques are going to be much, much more complicated because it's not just what's best for the concrete. I mean, if we look at what's best for the concrete, don't use de-icing salts, right? That's a great technique, but that's not very practical because we want to use de-icing salts to provide safety for the folks that are there. So I think really what we want to try to do is we want to try to make our system as salt proof or salt resistant as possible. One of the ways we can do that is through the mixture design. One of the ways that we can do that is through using topical treatments on top of the, there's different types of materials. We've done a lot of work with something called soy methyl ester. I know other people have said that's going to be very similar to things that have been used in the past, like a linseed oil. But what it really does is it coats the material and prevents that salt reaction. If you hit the system while it's dry with a lot of de-icing salts, that can create problems, and we try to avoid that. But I don't have any real specific stuff on de-icing salt recommendations.
All right, and this is maybe a question for a larger discussion here, but one comment here from a listener. Thank you, Dr. Jason, for this outstanding presentation. I would ask a question about the availability of slag, how we can ensure for the next generation that there's satisfied quantity if we don't use steel production as a source of slag, because the world will just use recycled steel.
Yeah, I would say that's a great question, and I think that is an awesome question that's probably being handled at the 130 Committee on Sustainability. What I would say is, for right now, we've got plenty of slag, as far as I know, that's available to be used, and I think this is a great application for it to be used in. What will the next 30 years hold? That's something we're going to have to chase down over the next 30 years. But I think for today, what I would recommend is utilize more slag in your pavements because it's going to make the joints more durable. And the other thing it's going to do is it's going to make your pavements last longer, which has a huge sustainability benefit as well.
One last question. What is the minimum amount of fly ash used to provide the same protection as 30 to 40% slag?
Yeah. So again, where I would go is I'd go back to this graph that now is a drawn-on masterpiece here. But what you notice here is the oxychloride is going to be the oxychloride versus SCM replacement level. If we want to be in this range of, let's say, 50% to 20-25% slag, which I was talking about, what you'll notice is the slag is really, really close to the fly ash. So in this region, we want to be between, usually, what I would say is 25 to 30% fly ash or slag, up to 50 is usually a practical point. Although somebody just mentioned why not go higher, and I think that would be fine. But you're going to be in that same range for fly ash. And where I would say, because this is a slag session, what I would do is I would say this is probably advantage slag, because slag is typically being used at these higher dosage levels and is being used more commonly in the field at those dosage levels. For fly ash to get into this range, I think we have to up the game on our fly ash replacement levels, and that's something that we've probably got to discuss. But I think here slag is really well positioned for that 30 to 50% replacement level to really do the job that it needs to be doing here.